Okay, Assalamualaikum and hi guys. So for this video, I want to explain to you on example 13.1. Okay, so let's say we have this tracer data is given to you. Okay, so you will have T and CT. So this is one example of question. Okay, was injected as a pulse to a reactor, right? So they want you actually to calculate construct figures showing CT and ET. Okay, so normally we don't ask you to construct figures. We normally ask you to calculate ET, right? But never mind. I still explaining the example 30.1. Okay, so you will see, right? So when you construct the figure, okay, so just now the data provided to you is T over CT. So you can construct a figure, a graph, CT versus T, right? So you will produce a C curve, okay? And then in order for us to calculate for ET, okay, if you look at the formula, so hold on, where is the formula for ET? So this is the formula ET, which I have explained earlier in our lecture note. Right, so ET is actually CT over CT, the curve of CT dt from 0 to infinity. So in the end, what you want is to build, to have this kind of table. So at different T and CT, we have ET, right? So in order for you to solve for ET, you need to calculate the area under the curve. So how are you going to calculate this area under the curve? Is actually by solving it using Simpson's method. Okay, so Simpson's method in this book formula, the old version is in Appendix A4. This is just the similar concept that you have learned in numerical methods or even in fraction 1. Okay, so let's have a look just now. Right, so earlier, okay, so how are we going to solve that? Okay, if you look in the question just now, there are two sets of H. Okay, so one is from 0 to 10, the H is equals to 1, right? And the second set is 10 to 14, where the H, the difference between one data to another data is 2. So that's why in this book, it is split to calculate the integral of CT from 0 to infinity. It splits into 2, alright? So the first one, you solve using Simpson's method. It's up to you. You want to use 5 points or 8 points. Okay, you may refer to the appendix, right? The second part is they're using 3 points or trapezoidal. So it's up to you as well. So total up, okay. So the total up from 0 to infinity. So this 47.4 plus 2.6, it will produce 50 gram minute per meter cube. Okay, next. So once you have that, then only you can calculate your ET. So meaning that ET at this point is 1 over 15. So it will produce 0.02. And then 5 over 15, so 0.1. So you calculate that for the rest of T and CT. So if they ask you to, if the question asks you to, construct a figure of ET, so ET versus T, so you get this value from the table you construct just now over versus T, right? So most likely the C curve and ET curve will have the same kind of pattern, right? So in example 13.1 just now, they ask you, the question also asks you to calculate the fraction from 3 to 6. So you just take the data from 3 to 6. So we refer to the table 3 to 6. So we take ET at 0.16, okay, 0.2, ET at 5, 0.16, and ET at 0.12. This is solved by using a Simpson's method, right? So in the end, you will get 0.51, meaning it's 51% of material leaving the reactor span between 3 to 6. Okay. So Right. So, okay, now I'm going to show you example 13.2. This is a continuous example from 13.1. 13.1, you calculate the ET. So in 13.2, the question asks you to calculate the means residence time and also variance. Okay, it's just the same set of data, right? So, right. So now, how are we going to calculate TM? Okay. So Tm is calculated by using this formula. It's TET from 0 to infinity. So you need to calculate, you have calculated already ET. So in the end, this is the kind of table that you will produce, you see. So initially the question gives you T and CT. And then from 13.1, example 13.1, you produce this column ET. And now you are calculating the TM. So you need to calculate first T times ET. So this one, you just multiply. For instance, 1 times ET, T at 1 times ET at 1, so 0.02. So this you need to calculate for the whole value, okay? Then you solve this, okay, similar as what you solved using Simpson's rule, like example 13.1, where you split the similar H, you put into this one method, and then another set of different H into another method, okay? So initially they use, I think, 3-8 and then trapezoidal rule. So you use this one, right? You need to have a constant Simpson's method. If earlier you decided to use 5 points, then for ET you calculate using 5 points. So TM also you use 5 points. So you need to be consistent, right? So if you have a look on this column, okay, this is for calculating variance. Okay, so variance is actually T minus TM square ET. So you need to settle for TM first, okay? So for this question, for TM, okay, let's have a look on the final TM value. So you see, so they solve it using Simpson's rule, alright? So this is only mathematics. You may refer back to your knowledge on CRE1 and also numerical method. So in the end, you get TM is 5.15 minutes. So you will use this TM to calculate your variance. Okay, so here, so you put, and then you just substitute your TM value here with ET, and then you will produce this column, right? So this one, they produce it one by one, and in the end, then only they arrive. This is the formula for variance, sigma squared, right? So let's have a look on the next value. Okay, so in the end, you will see variance is actually 6.19 when you solve the equation. Okay, so variance can be solved using two formula. One is this, another one, the one that I showed you earlier. Okay, both will give you quite more or less the same value. So variance is 6.19. If you want to calculate the standard deviation, which is sigma, is equal to 2.49, right? Okay, so now I want to show you another example. This is the question from previous semester test, okay, that I have shared with you without the answer scheme. So, okay, so we take this question. A first order liquid phase reaction is carried out in a reactor having volume 250 liter and volumetric flow rate of 15 liter per minute. Okay, so which resulted in having this pulse tracer data. Okay, if you look at the time, the H is 5 so there's only one set of H. So I will use one method of Simpson's rule only. Alright, so the question wanted you to determine the mean residence time. Okay, And then determine the efficiency of reactor at similar volumetric flow rate. So this one I will explain to you later, but this one is just similar at example 13.1 and 13.2. Okay, so let's have a look on the, I've made an answer scheme, but it's in the Excel. Okay, so more or less it's the same as manual calculation. So, alright, so we make a table, a new table. So this is where time and CT. So you want to calculate ET. So earlier we know that ET is actually equals to CT that over the integral of CT curve. Okay, so what we can do is now, okay, so this is the formula that I've already put in. Okay, so here is actually I'm calculating using Simpson's rule. So I've calculated using from this value up towards C5. Okay, so I split it into 3. Okay, and then this one I split it into 1, 2, 3, 4, 5. Okay, so this is 3 point, this is 5 point. Okay, so I will get a total of CT is equals to 257.33. So I will use that to calculate. Okay, you see here, this is just now C15. So you total up. So ET is actually CT over this. Okay, it's an integral, right? Okay, if you want to plot the data, it's the CT versus T, right? So normally I don't ask you to plot, right? So you will find your ET here. Okay, so for this value is actually you want to calculate your TM. Remember just now is TM is equals to the integral of TET. So it's just the same thing. I'm using the similar Simpson's method. See, this is 3 point. Okay, okay, that is 3 point, right? And this is 5 point. So I split into 2. You can also, it's up to you. You can use one type of Simpson's rule to calculate all together. More or less, it's still the same. So it will be plus minus a few percentage error. Okay, so in the end, you will get your TM is about 16.34. Okay. Okay. Now we go to the B part of this chapter, right? So we want to determine the efficiency of the reactor at similar volumetric flow rate. So earlier was given to you with this kind of volume, 250 liter, and this volumetric flow rate, 15 liter per minute. So they want you to calculate the efficiency. Okay. So initial, your tracer data run will give you TM at 16.3 just now, right? So here, so let's say earlier, what is the TM for this kind of reactor? So you know that TM in a closed system, TM is equals to tau, and tau is equals to V over V naught, where V is the volume, V naught is volumetric flow rate, right? So in the question, your V will be 250 liter here, given here, and your volumetric flow rate V naught is 15 liter per minute. So you will get around 16.7 minute. So if you compare to the earlier that you get for the first part A, it's 16.3. So you can say more or less the efficiency is still the same, almost 100%. So here the answer is almost 100%, 90 point something lah, 90.9 I assume. Okay, so that's 3 marks, but you need to show this kind of calculation, right? Okay, that's all. So I will continue on answering the part C in the next video. Okay, we need to learn the part B of chapter part 2 of chapter 4 first. Okay, see you.